I cannot join in person, but yeah, I hope it's also okay that this is online now. Yeah, so the topic of my talk is the separability problem for sets that are definable in the Presburger logic and for so-called Paragon automata. What this means, you will see in a few minutes. First, notice this is some joint work with Elias Collins and Georg Zetsche. And yeah, let's say next. Next slide, please. Okay. So before we start with all this stuff, we start with some introduction to verification problems. Next. Okay. The main problem in verification is, I guess, the reachability problem. So this is the problem where we have given some program P and two configurations of this program, C and D, and we ask whether there's a run of P starting in the configuration C and eventually arriving in the configuration D. Next, yes, thank you. Yeah, so for example, in this picture, this is a configuration graph of some program P, and we ask whether we can reach this state labeled with D from C. And yeah, we can see the reachable configurations are these orange ones, and so D is in this case not reachable. Next, yes. Okay. Why do we need reachability? Yeah, for classical correctness checks, like run the program P with input X, and we ask, is the output Y? Or run program P with input X, and will it throw an exception, E, as expected, or not? And next, a bit more generalized version of the reachability problem is then, yeah, given a program P and two sets of configurations C and D, and we ask whether there's a run from one configuration in C to one configuration in D. A related problem to this is the safety problem. Here, our input is, again, some program P and the configuration C and a set of configurations S. And the question is, for any run starting in C, are we always staying in the sets S? So we can see this as following. If you start in this one state, and where we always stay in the set of good states. Or in other words, is it possible to avoid these bad states? And this is actually what we want to check. Can you avoid reaching some undesired configuration, like an unhandled exception? And we can also see this as the complementary problem of the reachability, which means we check whether there's no run starting from C, eventually arriving in the complement of S. And then, yeah, next slide. There's also the separability problem, which is related to the safety problem. Here, the separability problem of two sets from one class C by a set from a class D is the following. We have an input two sets K and L from C, and we ask whether there's some set S and D such that this set contains completely K, but it is disjoint from L. Some examples. So we have two sets K and L, and in the first case, yeah, it's probably easy to separate these two sets K and L just by set S. Next, please. Yeah, so this is easy. The second case, well, in this case, K and L just intersect, so it's impossible to separate them, because there will be no set S which completely contains K, but it's disjoint from L. And in the third case, well, in this case, these two sets are disjoint, but for any possible separator S, we have the case that either it does not contain complete decay or it intersects with L. And so in this third case, it's also impossible to separate. And the existence of such a separator is also some kind of a certificate of the safety of a program. If we see the set K as a set of reachable configurations in P, and L the set of undesired configurations in our program P. And in my talk, we want to consider two kinds of separability problems. And the first one is on the next slide. Separability in Presburger definable sets. Okay, first, again, some short definition of Presburger logic. It is the first order logic of the structure N with natural numbers plus and smaller equal relation. And we have symbols 0 and 1. And a set S is called Presburger definable if there's a Presburger formula phi with d free variables such that S equals the set of all vectors which satisfy this formula phi. Then also the satisfiability problem is given the Presburger sentence phi, which means a formula without free variables, and we ask, does this formula hold in N? And we know from Presburger that satisfiability of Presburger formulas is decidable, and for existential Presburger formulas, this is even NP. And an existential Presburger formula is formula looking like this. We have a block of existential quantifiers, and then we have some formula psi, which does not contain any quantifiers anymore. Okay, then there are semi-linear sets. So a set S is linear if there's some vector U and a finite set P, such that S equals the sum of U and P iterated. And a set is called semilinear if it's just a finite union of such linear sets. And famous result from Ginsburg and Spanier is that a set is Presburger definable if and only if it's semilinear. And this equivalence is even effective. So in the following, we will use semilinear and Presburger definable for the same thing. And we also define some other kind of sets, which are recognizable sets. And a set S is recognizable if it is accepted by some DFA A, labeled with vectors instead of letters, such that we have the following property. If we have some path from P to R labeled with vector V and W, then there's also some path where we first read W and then V. Here's some example. This is such a DFA, and we want to know, is in this case the vector A1 accepted by this DFA? And there's, for example, this run. Actually, there are many runs labeled with H1. So we just sum up all these labels, and then we obtain H1, and if we start an initial state, we end in a final state. So this is accepting, and this word is in this case contained in this recognizable set. Click, please. Yes. Okay. And about recognizable sets, we know a set is recognizable if and only if it's definable by a monetic Presburger formula. And a monetic Presburger formula, click, or next, is a formula where each atom contains at most one variable. Okay, now it's time to state our first main theorem, which is given two semilinear sets defined by an existential Presburger formula. Then the separability problem via recognizable sets is Co-NP complete. First, let's talk about the Co-NP hardness. We do this by reduction from emptiness of semilinear sets, given as existential Presburger formulas. So let K be defined by some formula phi, and then K is empty if and only if K is separable from all vectors by a recognizable set. And this recognizable set is in this case just the empty set. Okay, now let's talk about the containment in Co-NP. But instead of showing the containment in Co-NP, we just show the opposite thing. We showed that the inseparability problem is in NP. So given two existential Presburger formulas, phi and psi, we will construct now another existential Presburger sentence in this case, G, such that this sentence is satisfiable in the Presburger logic if and only if the solution sets of phi and psi are inseparable by a recognizable set. This is what we want to do. And what we do first is we want to simplify formulas. So assume that phi and psi look like this. So we have a block of existential quantifiers, and then we have some formulas xi1 and xi2, and each of them contain no quantifiers and also no negation. And all atoms have to form some term and then greater or equals 0. And this is doable in polynomial time. So this is no restriction. What we know is that there are a bunch of formulas such that each of these formulas using only conjunctions, and I1 and Xi2 is equivalent to a disjunction of these conjunctions. In other words, we can transform these formulas into disjunctive normal form. But there's one problem. The number of these formulas is exponential, so we cannot compute all of them at the same time. Instead, we observe the following. So we can say the formulas phi and psi are inseparable if and only if there's at least one for each of these formulas, phi1 and psi j, which are inseparable. And we do the following. We just guess in polynomial time one one pair of these formulas, and we do this as following. Assume that this is the syntax tree of some formula phi, xi1 for example, and then we select atoms as following. If we see some, so we start in the root, and if we see a disjunction, we just go one to one of the children. If we see conjunction, we go to both to all children, and if we arrive in an atom, we just add this to our formula, and in the end, we just have the conjunction of all these selected atoms. So this is how we select these formulas. Okay, now we want to go from formulas to Diophantine equations. So as we've seen before, we can assume that phi and psi are now finite conjunctions of atoms of the form some term greater or equals 0. And by adding further variables, we can replace these terms by some new term equals 0. And then, yeah, we can also write our solution sets, in this case R and S, as some solution set of some linear equation system AX, B, and CY equals D. And okay, we introduced some new variables, so we have to project them out. So this is some projection from the set of all variables in this equational system to the coordinates you're really interested in. And yeah, we can observe the sets R and S are so-called hyperlinear sets. And a set is hyperlinear if it has the form some set A plus U iterated, where A and U are just sets or finite sets of vectors. So this is something in between linear and semi-linear. Okay. So now let's talk about some idea for simplification of the separability or inseparability problem for hyperlinear sets. So assume that the set R is bounded at some coordinate J. This means, yeah, that there's some value M such that each vector in R has at coordinate J a value at least, at most M. Then we can observe that R and S are inseparable if and only if there's some value X from 0 to M, such that if you take S and R restricted to only those vectors which have the value X at coordinate J. Then R and S are inseparable if and only if these restricted sets of R and S are inseparable. And actually we also project to the coordinates without J in this case. So we just simplify R and S. And what we can do is we just guess such a value S, X, and then continue with these restricted sets. Similarly, we can also do this with S, of course. But there's a problem. Yeah, the construction of these sets is very expensive. So we won't do this here because we cannot do this in polynomial time. Instead, we do the following. Okay, before we do the following, some new notion. A vector for vector v, the support is just a set of all coordinates J, where the value in this vector is non-zero. And yeah, now let R and S be so that they are hyperlinear. So we can write them as A plus U star and B plus V star. And we just do something similar to the algorithm from the previous slide. So repeat the following until stabilization. For each coordinate, we say we do the following. So if S is bounded at coordinate J, then we remove all vectors from the all period vectors from R, or actually from the set U, which have support on J, so which are non-zero in this coordinate. And similarly, we do this for R. If R is bounded at J, then we remove everything from S, which has support in this coordinate. And all the remaining coordinates, which are unbounded, are now called strongly unbounded. And by J, we denote the set of all strongly unbounded coordinates now. And by Uj and Vj, we denote the sets of all remaining vectors after this procedure here. And then we can show, or we will not show this here, but we just state this, the following. So if R and S are now two hyperlinear sets, then R and S are not separable by a recognizable set if and only if this strange intersection here is not empty. Well, what does this intersection mean? Click. Yeah, so the first term here can we understand as R extended by the group generated by the vectors in Uj. So now we also have so no, how to explain? We just take R and remove something from this again. The thing is, here we are talking about vectors over integers, and but it's maybe a bit problematic. So instead, we do the following, which is just equivalent. We say that R and S are not separable if and only if, just by adding Uj star and Vj star to both sides, we obtain this intersection, and this is a bit easier to handle because now we are talking about natural numbers. But it's equivalent, and we will use this fact now on the next slide. Okay, so recall that R and S have this shape. So these are solution sets of the equations ax equals b and cy equals d. And R and S are inseparable if and only if this complicated intersection is non-empty. And what you can show is that R and S are inseparable if and only if there are several vectors u, v, x, and y with the following properties. U and v are solutions of the homogeneous system ax equals 0 and cy equals 0. And they have the same support. And the same support is some hint to we are in Vj and Uj. So this is some so this means U and V are some elements from Vj and Uj, and then we also have X as a solution of the inhomogeneous system, and also Y is a system of this inhomogeneous system of equations. And we have X plus V equals Y plus U. Okay, only projected to interesting coordinates. And this finally means, yeah, we have something in this equation here, in this intersection. And the good thing is, this property here, this can be expressed in an existential Presburger formula psi. And this formula is satisfiable if and only if R and S are inseparable. Click, please. Yes. And we also can compute this formula from phi and psi in non-deterministically polynomial time. And also satisfiability is in NP. So everything is in NP. Okay, how much time do we have got? Okay, now let's talk about separability in periodic automata. So click, please. Before starting introducing periodic automata, let's motivate them with Peric's theorem, or actually the Peric map So let sigma be an alphabet. And the paired map is some function which maps words to the number of occurrences of each letter in this word. And the paired image of some language L is then just the set of all vectors or all paired images of each word in this language L. And Perek's theorem says that the paired image of context-free languages is semilinear. So now again, we are related to semilinear sets. And paired automata are the following. We have some tuple, where the first item is some epsilon NFA A and some semilinear target set C. And a word W is accepted by this paired automaton if and only if there's an accepting run in this automaton, which is labeled with this word W, and the paired image of this run, where we count the occurrences of transitions, not of the labels. If this paired image is in our target set C. Let's look at this example. And our target set is now this set C. And we have this automaton here. We have 5 transitions, so we need 5 counters, and we want to check whether this word AA, BB, CC is accepted. So that there will be a lot of clicks now. So we start in Q0, and first we read an A. So we do this loop here and add our counter by 1 for the first transition. We do this again. So we have counter value 2 now. Then we go to the next state via this epsilon transition. So we increase the second counter. Then we do 2 times this loop at B. And we go to the last state, and again we are doing this loop twice. And we arrive in some so now we have the paired image of our run 2 1 2 1 2, and this is contained in C. So, and since we are also in an accepting state, our paired automaton accepts the word AA BP CC. And the interesting thing is the emptiness problem for paired automata, where the target sets are given by existential Presburger formulas, is NP complete. And this is also what you need to know. Well, our second main theorem we want to prove is the following. The regular separability problem for paired automata is co-NP complete. This is what we want to show. First, one note, decidability of this problem was already known. This was shown by Clemente et al. At ICLA 2017. But in this paper, they did not say anything about complexity, or actually they just gave some very high complexity upper bound. But this was not the best guess of the complexity. And here we show that it's even in co-NP. But first, co-NP hardness. This can be shown by reduction from the emptiness problem for paired automata. And for a given paired automaton, its accepted language is separable from the set of all words. This is possible if and only if the accepted language is empty. Now let's talk about containment in co-NP. Or actually, we showed that regular inseparability is an NP for these paired automata. So let AC and BD be 2 paired automata. And what we do is the following. in the first step, we construct in polynomial time DFA C. So this means some deterministic automaton and a semilinear and two semilinear sets E1 and E2, such that the languages of our two Tarek automata are regularly separable if and only if the language is accepted by C with target set E1 and C with target set E2 are regularly separable. So what we did is first we determinized our automata, which is very interesting because typically this will give some exponential blowup. But here we don't say we have the same sets of languages. This the same sets of words. So these are two new languages, but we still have this equivalence. And yeah, so we have one deterministic automaton here with two different target sets in this case. And the second step, let's observe that there are hyperlinear sets, R and S, such that the languages of these two Peano automata with same underlying DFA are regularly separable if and only if R and S are separable by a recognizable set. And here, the sets R and S is are the following. We just count the simple cycles of our automaton C on accepting runs. So this means for each simple cycle, we have one coordinate in R and S. And also recall, since these are hyperlinear sets, yeah, that again, we can use this that they are inseparable if and only if this complicated intersection is non-empty. The only thing is we cannot use this sets R and S because the number of simple cycles in C is exponential, and so we cannot compute R and S in polynomial time. Instead, what we do is first we need to find out Vj and Uj, and for this we just guess these sets, or actually the set J. Or actually we don't compute the complete set J because this can also be exponential. We compute only transitions participating in these cycles. And this is possible in polynomial time. And finally, we construct from our DFAC and its target sets E1 and E2 in polynomial time a Peano automaton, DNF, such that this Peano automaton accepts at least one word if and only if this complicated intersection is non-empty. And this is all we have to prove. We don't want to do this here because we don't have time anymore. And so I want to come to an end now. Thank you for your attention. And yeah, are there any questions?
We have time for one quick question, maybe. Anyone? Okay. Yeah, sure.
Very trivial maybe question. In the last line, we have A plus U star plus V, and previously I remember we had minus in the expressions when we considered not Peano automata, but in the first part of your talk. Maybe this is the same thing, but...
yeah, that was a slide a long time ago.
So here.
You found it, yes. So yeah, actually what we have in the first thing, if this set is if this intersection is non-empty, then we have just some equation of some element in UV minus some element in UJ star equals some element from b plus v star minus some element in vj star. And this can be also written as, just this element from au star plus the element from vj star equals the
Okay.
remaining stuff. So this is why this is equivalent, these two things.
And one maybe very, very simple question. And what papers do you cite when you use NP upper bound for existential Presburger arithmetic?
That's a very good question. I don't know who proved this. I should find out this, but
Okay, thank you.
Someone proved this at least once. I think it was not Presburger.
When he died, Presburger died much earlier than the class NP was defined. In 1970, it was defined by Kuka, and Presburger died, I suppose, in 1942, 44. I don't know.
Yeah, right.
It was impossible.
Yeah. So I think it's also by von Zurgathan. I mean, it is an implication by a theorem by von Zurgathan and Saiwei-King, who gives a small model property for linear different inequalities. So you can basically use that and that, and you get the solution. So so basically the result is because of some work in interior linear programming rather than so thanks a lot, Chris, for bearing with this technical glitch. I mean, whatever.
I also have to thank you.
Yeah, you should thank me. Okay, no, just kidding. Thanks a lot. And now, is it okay to record the talk? I mean,
yeah, that's fine. I just wanted to know whether you can hear me fine.
Yeah, everything is fine. I think we can hear you.
Okay. Well, thank you for for inviting me. I'm sorry that I could not be there. So this is an old work from 2022 with Dimitri Chisikov from Warwick and Christoph Hasse from Oxford. And as the title suggests, we will look at a geometric procedure for Presburger arithmetic. Now you have already probably saw already quite a bit of Presburger arithmetic in the previous talks. So let me not really do it again. The only thing that you must know for this talk is that one of the motivation is that for many applications, well, you don't often need to actually solve satisfiability. So knowing that formally satisfiable or not is important, but for many applications, you actually want to compute an object or compute property of an object represented by the our Presburger arithmetic formula. For instance, there is this very nice paper by Veduliagi in Arithmetica 27, where it takes some problem from compiler optimization, which is about how many times a loop is executed, and it compiles it down to a certain function that takes as input the input of the program, and then it wants to compute the number of solutions of a certain Presburger arithmetic formula. So here we want to really be able to not to just say satisfiable, to count the number of solutions parametrically on an input. And one of the key results when it comes to this type of questions is a theorem by Ginsman-Spanier from 1966 that every set defined in Presburger arithmetic coincide with the family of semilinear set that was also present in the previous talk. So let me in 1 second give you a bit of a more, let's say, long introduction on semilinear set, because we will use them a lot. So they need to be clear in your mind. So semilinear set, they can be thought of some sort of extension of arithmetic progression to multiple dimensions. So in arithmetic progression, you usually have just 2 vectors, a base point B and a period P. These are just numbers, in fact, because we are in 1 dimension. And the arithmetic progression is built starting from the base point B by just iterating the period P a non-negative amount of times. And they will define in this way a subset of the natural numbers. You can extend that to several dimensions. This is what is called a linear set. And this is still 1 base point, but now we have many periods, more than the dimension even. This is a semilinear set. Then we have a linear set, and this is a semilinear set, which is just a union of semilinear sets, of linear sets. So now you have multiple bases and multiple periods. And I will sometimes call this, define a linear set with this notation LBP. And this would be one component of the semilinear set. Now, the theorem by Gisman-Spanier shows that essentially, semilinear sets are closed under union, projection, and complementation. Now, together with the fact that if you take an atomic formula of Presburger arithmetic, you can construct an equivalent semilinear set. This shows that essentially all formulae of Presburger arithmetic are semilinear or define semilinear sets, because you can simply apply the translation on the atomic formula and then apply the translation for union, projection, and complementation in order to handle disjunction, quantification, and negation. Now, if you look at this on an algorithmic point of view, meaning that you really want to do the translation on a procedure, on an algorithm, there is one big problem, which is the complementation algorithm. Meaning that, of course, if I take two semilinear sets and I want to compute the union, that's trivial. I just really put the union together. This is just union of linear sets. If I want to project, I just need to cross out one dimension from the semilinear sets. From every vector, I remove one dimension. But complementation is more complicated, and most of our talk, of my talk, will be on complementation. So, in particular, we will discuss an optimal algorithm for complement semilinear sets, and this algorithm has some effect on kind of the theory of Presburger arithmetic, which is to kind of put the complexity of a geometric procedure as being the same as the complexity of quantifier elimination and automata procedures. Now, the fact that quantifier elimination is doable in triple exponential time is a result of open. Then later in the early 2000s, people discovered that also automata that were firstly introduced by Bucci can be used to solve Presburger arithmetic optimally in 3 exponential time. And this result kind of does the same for geometry, for semilinear sets. Okay, so our goal is to try to complement a semilinear set. But before doing that, it's helpful to look at what we can do over the reals instead. So we will take a linear theory of the reals. So essentially it's Presburger arithmetic, but now we work with the reals, the variable range over the reals. And we will try to kind of do a complementation of whatever the formula over the reals represent. And if you are a bit familiar with kind of Tarski arithmetic, which is the extension that also features multiplication, in Tarski arithmetic, a critical algorithm is cylindrical algebraic decomposition. It's an algorithm by Collins that essentially divides the region into cells and then decides what cell to be taken when you do a complementation. This will be the same just on the linear case. So to complement over the reals, I need two ingredients. The first ingredient is a theorem by Minkowski-Weil that essentially gives you a way to change a representation between objects. So the Minkowski-Weil theorem says the following. If I have a system of inequalities over the reals, here is this H. I don't know if you see my cursor, but is this H here. I can construct from it two finite set of vectors, V and W, such that the convex hull of V plus the conic hull of W form the set of solution of the system of inequalities. And vice versa, every sum of a convex hull and a conic hull can be translated into a system of inequalities. That are the same solution. Now here, this sum is the Minkowski sum, meaning that for this V representation, vertices representation, what I will have is that I take the various vector, build the convex hull, build the conic hull, this is W, and then I just take every point from the two, sum them, and it will give me my convex polyhedron that is represented by the system of inequalities. Now we're interested in algorithms. So what we're interested in this theorem is kind of the algorithmic aspect of it and the complexity of it. And here I have some very ugly notation probably, but it's something that it will turn out to be kind of always the same throughout the talk. So let's at least once do it properly. Whenever you take HRV, it doesn't matter, the blow up is the same. The bit length of the number in the output will be just polynomially bounded by the input, where we got a factor of poly d, which is a polynomial in the dimension. So essentially, when you do the translation, no matter what direction you use, the bit length explodes a bit, but not too much, not significantly. This is very important. Now, what instead is a bit worse is the amount of number that you have. Like, for instance, you start from a very small matrix, here A. Now I need to tell you how many vector V and W you need to have, like not the dimension, but the number of them. So the amount of numbers that you have is the amount of numbers that you have at the beginning, the input, but exponentiated by a d. So is exponential in d. And here I'm using this weird Nutaro notation where essentially I'm hiding polynomial factors when I use it. So the real will be number of numbers in the input to the poly d. And every time that you see an up arrow, there is always a poly something somewhere hidden. So for instance, when I do it from B to H, what happens is that the matrix, the bit size of the number in the matrix just explode in the dimension. And the amount of numbers, so how big is the matrix, will be exponentially in the dimension. So this is my first ingredient. I want to translate from B to H and for H to E. Another one last thing that just to recall, remember that by supporting hyperplane, we mean an hyperplane that kind of is such that the polyhedron is full inside one of the two half space of the hyperplane. So here is kind of intuitively what a supporting hyperplane means. We will need that later. The second ingredient is a very nice lemma about cutting the region using hyperplanes. So this is kind of the question we start with. We have our space, R to the D. We use n hyperplanes. And I want to discover what is the maximum number of parts in D dimension that I can generate by cutting H to the RD using n hyperplanes. And this will be this pi dn that I have here in the slide. So if I do it for one hyperplane in arbitrary dimension, this is always 3. That's fine. And I'm counting also lower dimensional region. So when I have one hyperplane, I have one space open in kind of to the left of the hyperplane, one to the right, and then I have the hyperplane itself. It's 3 regions. Now let's kind of put that in some sort of recurrence system. So when I have 0 dimension and n hyperplane, or I have d dimension and 0 hyperplane, I have only one region, is my ambient space. If instead I have d plus 1 dimension and n plus 1 hyperplanes, this number of region is always below what I obtain by doing d plus 1 dimension and n hyperplane, so one hyperplane less, plus twice the number of region that I have for d dimension d and n hyperplanes. And now I want to give you the proof of why this is the case. So let's start with the picture on the left, where let us assume that this is we're in dimension d plus 1, and we used n hyperplanes. So is this initial one at the right on of the less than equal. Now I want to understand how many region I will add when I add the last hyperplane, the n plus 1 hyperplane. So is this hyperplane here? Is this one in green? And one thing that I notice is that if I look at a previous region that I have, only the blue-red region, and I add the green one, now I'm cutting the region into 3. So there was one region, and now it's 3, so I added 2 regions. So this is the plus 2 that you see here. And I add 2 regions every time that I intersect a region with my new hyperplane. So now I want to know essentially how many intersection does this hyperplane that I added has with respect to the previous n hyperplane that I have before. And this, what I do is that I imagine living inside this hyperplane green. And if I live inside this hyperplane green, now I'm in dimension D, and I will see the intersection as hyperplane in dimension D plus D minus 1. So the hyperplane of dimension D. So the number of intersection is this phi dn. And in this way, I get this recurrence relation. I solved it, and I find that actually the number of region when I have dimension D and I cut with n hyperplanes is always kind of bounded exponentially in D, but polynomially in the naiper of hyperplanes. And I will call this later n to the D cutting lemma. Now, this lemma is very powerful. In fact, if you look at the literature, it's used very often in different ways. And one of the reasons why it's very powerful is that it allows to put formula from linear arithmetic, Presburger or reals, doesn't matter. It will allow you to put the formula on a linear arithmetic in disjunctive normal form with polynomial disjunctions in fixed dimension, meaning if I only care about formula with 3 variables, I only look at the problem with formula in 3 variables, I can take the formula and put it in dimension in disjunctive normal form, and the number of digits that I will get, it will be cubic. It will be n to the 3 here. And the reason is that each disjunct in a DNF represents one region of this kind of partitioning lemma that we did. So, but coming back to our complementation, now I have 2 ingredients. I have Minkowski-Weil, and I have the n to the D cutting lemma. So let's see how we kind of complement one such set. So I take a union of convex cells and conical. So these are kind of the V representation in the Minkowski-Weil theorems, a union of them. And you can see them as kind of real version of semilinear sets, right? I have a union, I have my base vectors, and I have my period vectors. And let's see how we compute it. So what I will do is that I will first find a family of hyperplanes that carves out all my polyhedron. By carving out, I mean that if I look at a certain region that is cut by the hyperplane, the region is either fully in the set or fully outside the set. And in a sense, I can, from the pieces of my region, I can reconstruct my union of polyhedra. So I find this one. And then what I can do is that I can just pick region by region, one sample from each region, also the lower dimensional one, and decide whether it was from the set, from just that one sample. I can decide whether the whole region was in the set or not in the set. And I can decide to take it or not to take it, depending on whether I want the complement or the set itself at the beginning. To do this algorithm, we use we will use the Minkowski-Weil theorems and then to the cutting lemma. But it is helpful now, because we want later to do it over the integers, to one second, sorry. It is helpful to kind of clarify a bit more what I mean by carving out the polyhedron. So let me introduce a notion that is a bit of a kind of a mouthful, but let's go on. That is the notion of an R splitter. So an R splitter for a certain family of convex polyhedron P, and this P will be this set here, will be a family of convex polyhedra R that one, it generates all RD when I take the union of all my convex polyhedron in R. And R must be closed under taking phases. Furthermore, if I take 2 regions, let's call them 2 polyhedron in R, and I look at the intersection, this intersection is either empty or it is a phase of both R1 and R2, so it is a lower dimensional phase. Third property that I need in order to do the complementation is that if I take one region R and one polyhedron P and I intersect them, again, either I get the empty intersection or I get a phase of R. This is what I meant by carving out a polyhedron before. When I have such a division of RD, Then I can do the algorithm that I explained, where I take the various spaces and I try to locally understand whether one or not is in the complement of my set. We can then look at the complexity of this and discover that if I start with a particular union of polyhedron over R, then I can find an R splitter. Again, it will be convex hull of certain vectors and conical of other vectors with the Minkowski sum. And again, I get a very similar bounce that what we were getting with Minkowski-Weil and with the n to the d cutting lemma. The bit size, very good, no explosion at all. The number of regions that I need is exponentially in the dimension. And the proof of this theorem is really just Minkowski-Weil plus the n to the d cutting lemma. So this gives us a way to complement over R. Now I will try in the short time that is left to explain how we go from R to Z, and in particular, how I need to change the definition of R splitter in order to obtain a Z splitter, a splitter for Z, for the integers. First of all, let's recall that, okay, we use the Minkowski-Weil theorem. We don't have analogous for the integers, meaning we have one direction, but not the second. There is this very nice theorem by von Zurgaten that essentially says the following. If I have a system of inequalities over Z, then I can construct from it a semilinear set, where in particular I'm using always the same period across all components of the semilinear set. So I have several base points. This is the set B, and the same period across all. And this is kind of how it looks like you will have the various base points, so not anymore a convex hull, just the base points. You have a discrete cone now, and this is the shape that you construct. And you can see that now I can go from H to V, but it's very difficult from going from V to H, because if I give you this object on the right, now you will need to be able to represent it with a system of inequalities, and you simply cannot, because, for instance, you see I have these gaps here, and there is no way to construct a convex object, a system of inequalities, that represent these gaps, that kind of will not fill these gaps. So when I go from the reals to the integer, I lose one direction of Minkowski-Weil. I can go H to V, but not V to H. This will not be a problem, but it's something to keep in mind. The cost of switching, very similar to before. The only thing is that the number of points now is not only of base points, is not only the exponential in the dimension, but also on the bit length of the number that this is a typo, should be A. Bit length of the number that I have in the matrix. No, it's correct. Sorry, it is that then it's that. Yes, it's bounded by that. Exponentially. So it's a bit of a worse bound, and this is something that in practice in the paper we need to take care of a lot, but it's not something that I can give you here in a few minutes. So, okay, first thing, Wolfgang Sevenking, a very nice result. In the following, because this notation is particularly unfriendly, I will simply call this an hybrid linear set, which is something that also was done in a previous talk. So whenever a semilinear set has all periods the same across all components, I will call it a semilinear set. And I will denote it like this, LBP. Here I have again the same slides to let you understand, but I don't think I need to go on because you already saw this several times. Just remember that now I have a linear set, hybrid linear set, just shift of linear set, same base point, multiple periods, and then I still have semilinear set. And from now on, I can speak of a semilinear set as being a union of hybrid linear sets instead of linear sets. So now let's go to Z splitters. Let's start with the definition of R splitter. And I want to kind of slowly develop the notion of Z splitter by changing the definition of R splitter. So the first part of the R splitter was that essentially we were doing some sort of partition of R to the D. Now we cannot really partition R to the D with kind of closed objects. So that's why we had to say, oh, it's closed under taking faces, and when you take an intersection is either empty or a face of both. What I really wanted to do here is a partition. I could not. But now in Z I can, because of course it's not dense. So let's let's first change what I want. Sorry, I forgot about this slide. Let me change what I want. So instead of an R splitter, I want a Z splitter. It will take as a family of hybrid linear sets, P, and it will produce a family of hybrid linear set Z. And what I want as a goal is that I can compute easily P, or the union of P, using Z. So again, as I was saying before, the first part of the R splitter is that I wanted a partitioning, but over R, I cannot have an easy way to define that without getting too much, a lot of troubles. So then but over Z, I'm not dense, so I can do much easier. We can ask that each two of the hybrid linear set in Z are disjoint, and the union of them should be ZD. So I'm really partitioning ZD. Now I added this second criterion, and this is where we will need to work quite a bit. So the second criteria, I remember that it was about carving out polynomials, carving out polyhedrons. So you were taking a region, you were taking a polyhedron of your initial set, and then when you were intersecting them, either it was empty or it was a face of R. I cannot do that anymore, of course. But now what I can do instead is the following, is I can impose into Z the fact that for every linear set inside the hybrid linear sets, so here I need to also look at every base point inside a certain BI, my Zj, my subregion of Zd, is either fully included in the real approximation of the linear set B plus comp P, or it is fully excluded. And here I'm using a real approximation. This is the conical of Pi. So let's look how it looks in this example. So let's say that I have two linear sets like this. Now one region, these are kind of the supporting hyperplanes of the two cones over the reals of these two linear set. And one region could be this white region here. It is good because, of course, it will be full inside both the real approximation of the two linear sets. So I can take this as a region, but now let's remember the last property that I want, which is that I want to be able to compute easily, given a certain region, the complement of my semilinear set. So I have this region, and the idea would be that I want to complement it. So I can give you, and it should be an hybrid linear set that I want, each region. So I can give you many possibilities. I could give you this semilinear set here. It is covering my region, so that's fine. I will be able to then partition Z to the D if I do the same for every other region that I'm missing in this picture. But then I have a problem that I kind of lost too much information by doing this, and I'm not able to compute the complement locally to this region. So how do we fix this? The idea is the following. I would like to define Z to have the following property, that it will have, of course, a certain set of base points, a certain set of of periods. But when I want to intersect it with a linear set from my original set, I want the property that the intersection can be done by just intersecting the base, the set of vectors here. And this is a very simple operation because C is finite. So in particular, I can just iterate every vector in C and then check whether it was in a linear set. And the idea is that if I do that, then doing the opposite of this, so essentially taking every point that is not in this intersection, will complement my linear set. So to do this, for every I and for every B in BI, so for every linear set that I have in my region, essentially this is the idea. The idea is that I would like to find a window. Here is this with dashes. That kind of for which my region, when I look at the semilinear set inside it, is regular with respect to this window. What I mean is that if I have a point inside this window, and I translate the window by its height or its width, I get again a point in the set. So to do this, the easy way is that I can take as period sets the kind of a sort of LCM. It's not exactly an LCM, but in 2 dimension in this way, it works very well. The LCM of the periods in the original set. So here, for instance, this vector here is is 6, and it is just 2 times 3, which were the LCM of these 2 vectors.
Alex, sorry to interrupt. We just have 2 minutes. I mean, can you do?
Oh, sorry. My counter was 5. Okay, sorry. Okay. Once you find these 2 windows, you are able to complement very easily the semilinear set by simply essentially taking all the base points in this window here that were not original in your set, and this will complement right away the semilinear set. You do that for every region, and you're done. This is the complexity. Let me not go through it. The key point is that it's only exponential in the dimension, which is what we wanted to achieve in order to stay in 3 exponential time. So to kind of finish, the full algorithm goes like this to complement the semilinear set. You first take the input semilinear set. We will do first a step that I could not explain, but essentially it makes all the periods in the semilinear set proper, meaning of independent vectors. This is done with the Caratio-Dori theorem. Then you compute the Z-splitter. You compute you take the base point in the Z-splitter. You eliminate the set from the base point. This is easy because CJ is finite. And then you put together all the components of the semilinear set that you construct that have the same period. So you take a certain 2 points. If the 2 linear sets have the same period, they need to be in the same hybrid linear set, so you put them together. And that gives you the complementation algorithm. And to conclude, essentially, from this complementation algorithm, you can obtain that you can obtain an optimal procedure for Presburger arithmetic that has the same feature complexity-wise as quantifier elimination and automata. There is a bit more that I wanted to do, but since I have no time, you can check the paper. It's this paper here. Essentially, this is also the only procedure of the 3 that allows you to close a certain conjecture in Presburger arithmetic about the learnability of Presburger arithmetic in terms of its BC dimension. I will not go into details of this. Well, thank you for letting me talk about this. Sorry for being a bit maybe quick. And if you have some question, please ask.
Thank you, Alyssa, for a very interesting talk, very graphical. So we have time for one quick question, maybe. Yeah.
Thanks a lot for the talk. I have a question about when you're talking about in the real side of your picture. I mean, several kind of questions about, so when you go from this V to H, you say that there is this kind of a blow up. Is that known to be optimal in the sense that is it possible that we do better?
No. Everything is optimal here.
I see. Okay. So these are bounds all of
for both real and integers. Everything that it was in the talk is optimal.
I see. Okay, that's interesting. Yeah. Okay. Thanks a lot.
So as this was quick, if are there any other questions? We can take one more probably. Oh, if not, I have one question. So this was basically for the full class of P, right? I mean, but what if you have fixed number of quantifiers? Can you basically get this result? I mean, easier argument using geometry rather than? I mean, there is a known result, right? That it spans the whole weak exponential hierarchy, right? For a quantifier alternation, right?
Yes. So
can you use this kind of argument to? I mean, is it generalizable?
Yeah. So yes. So in general, if you fix the number of alternation, you drop exactly like quantifier elimination. The bounds are really the same. If you fix the number of variables, then You also drop the same. Yeah, no, it's really the same. The only thing that maybe is difficult to prove with this result is that there is a nice result of Nguyen and Pak. It's called the Short Presburger Arithmetic is Hard, the paper. And this result essentially says that even if you fix the number of variable, you fix the number of atomic formula, you fix the number of alternation, the only thing that you don't fix is the coefficient in the formula. You still climb the polynomial hierarchy. This type of result, I think this is difficult to prove with this. I mean, no, of course, yeah, the upper bound will not work right away. Yes. That's a very powerful result. It's in stock 2020 or 19, I think.
Oh, thank you. Thanks a lot for the talk. It was really interesting. So yeah, I'd basically like to conclude the session by thanking all the speakers and the attendees. I know for the fact that, all the speakers wanted to come, they tried to come. And I mean, we have two, Togrul and Chris, they applied for the visa, they didn't get it. Chris basically also booked his flight, I know that. And he was waiting for the visa till the last minute, but he couldn't make it. Alessio also wanted to come, but he because of his health, he couldn't come. And in spite of his health issues, he basically took some time early in the morning and gave us a talk. And Mikhail basically took a lot of his time, and he kind of was really took a lot of effort. Very, very nice talk. He also introduced something. I asked him to introduce Presburger Arithmetic just one day ago, and then he basically spent, after traveling for about 24 hours, he always spent about, half a day to, add those slides and all that. So thanks a lot for that. So thank you very much. And thanks a lot to for attendance. And I hope that, this come up. I mean, this basically encourages some more collaboration amongst, people present here. And so, okay.
And I think we should give a big round of applause to Raj for really putting in, we've been interacting and he really took a lot of pains to kind of get this very, very, remarkable set of people having works in such top conferences and, cutting edge work. So I think it is really hats off to him to have put together this entire workshop.
I think my work was easier because I had speakers who were dedicated to this community and, basically in spite of being close to the deadline which they usually publish. ICLA deadline is just 1 week ago, and today's CAV and the Lix was just last week.